my dear students. Today topic is zero potential point and relation between E and V, that is electric field intensity and potential. So first of all, what is meant by zero potential point? That is the point at which the total electric potential is zero is called as zero potential point. That is, first if you can write zero potential point, that is the point at which the electric potential, the total electric potential is zero is called zero potential point. The point at which the total electric potential is zero is called as zero potential point. Here, can we get a zero potential point with like charges? The answer is no. Here, first point in that case 1, for like charges, zero potential point cannot exist. Because if you consider two charges, this is Q1 and this is Q2, and these two are separated by distance. Now if you consider a unit positive charge at a point P, here this is X and this is D minus X. Then the total potential at point P is given by V1 plus V2, which is not equal to 0. Because this charge is positive, this charge is positive. If the charge is positive, potential is positive. If charge is negative, potential is negative. But here both are positive charges, so that the zero potential point cannot exist. But whereas in case of unlike charges, the zero potential point can exist at 2 points. One is in between the line joining the two charges, and another one is outside the line joining the two charges. And what are the expressions for it? Next one is case 2. For unlike charges, zero potential point can exist at 2 points. In that, the first point is in between the line joining the two charges. The second one is outside the line joining the two charges. So, in case 2, the zero potential point can exist at 2 points for unlike charges. One is in between the line joining the two charges, and another one is outside the line joining the two charges. So, how to calculate this? In that first one is in between the line joining the two charges. For that, let us say you are supposed two charges Q1 and Q2. Let us say this is plus Q1 and this is minus Q2, and whereas Q1 is less than minus Q2, separated by a distance. Then the 0 point is existing at point P at a distance x from this, then it is at a distance of d minus x. Therefore, here let Q1 and minus Q2 be the charges separated by a distance d. Separated by a distance d. Let the zero potential point is obtained at a point P at a distance x from smaller charge Q1. This is what you are going to take. And once you got it, then here, once you have obtained this, the total potential, therefore, you can write that at zero potential point. At zero potential point, what you are going to get? V is equals to V1 plus V2, that must be equal to 0. That is the total potential at point P, you can say it's 0. Therefore, V1 minus V2. This we can write this as, once you got this one here, V1 is equals to minus V2. That is 1 by 4 pi epsilon naught. Q1 by x is equals to minus 1 by 4 pi epsilon naught minus Q2 by d minus x. Therefore, d minus x by x is equals to Q2 by Q1. Or d by x minus 1 is Q2 by Q1, which implies d by x is equals to Q2 by Q1 plus 1. Therefore, x is equals to d by Q2 by Q1 plus 1. That is given by, it is nothing but separation between two charges by square bigger charge by smaller charge plus 1. This is the zero potential point when you come across the, in between the line joining the two. So, in the case of electric null point, there the point at which the resultant electric field intensity is 0 called as the electric null point. It is a vector quantity. So we have to consider resultant field. The point at which the resultant field is 0, that is null point. But here potential is a scalar. Therefore, if the total potential at a point is 0, that is called as the zero potential point. And here the second one is next one is outside. Second point what I have given is outside the line joining the two charges. Outside the line joining the two charges, please suppose here, if you consider this and this is Q1 and this is minus Q2. Now the zero potential point is obtained at a point P where you can assume a unit positive charge. So if this is D and this is x. This becomes d plus x. Therefore, at zero potential point, that is at P, V1 plus V2 should be equal to 0, or V1 is equals to minus V2. That we can write 1 by 4 pi epsilon naught Q1 by x is equals to minus 1 by 4 pi epsilon naught minus Q2 by d plus x. Therefore, d plus x by x is equal to Q2 by Q1, or d by x plus 1 is Q2 by Q1, or d by x is Q2 by Q1 minus 1. Therefore, x is equals to d by Q2 by Q1 minus 1. That is again separation distance between two charges by bigger charge by smaller charge minus 1. So these are the two cases. In case of electric null point, for like charges, the electric null point will be located in between the line joining the two charges. And for unlike charges, the electric null point will be located outside the line joining the two charges. But whereas zero potential point, when you consider, for like charges, zero potential point cannot exist. But whereas for unlike charges, the zero potential point can exist at 2 points. One is in between the line joining the two charges, and another one is outside the line joining the two charges. And how to calculate that we are given. Basing on this, you may be given a problem. You may be given that an example that two charges plus 2 microcoulombs and minus 8 microcoulombs are separated by a distance 12 centimeters. Find the zero potential point from the smaller charge. Find the distance of zero potential point from the smaller charge. First fundamental thing is here, if you can observe, this is plus 2 and this is minus 8. So these two are unlike charges. So definitely zero potential point will exist. Suppose you are given plus 2 coulombs are bind, plus 8, both are positive or both are negative. Then straight away there is no need to do anything. We can simply say zero potential point cannot exist. But here these two are unlike charges, so you can get the zero potential point at two steps. So first one is in between line joining the two charges. If you are going to calculate for this, then what you are going to get? X is equals to d by Q2 by Q1 plus 1. That is 12 by 8 by 2 plus 1. 2 1s and 2 4s, 12 by 5. That is given by 2.4. Therefore, x is equal to 2.4 centimeters from plus 2 microcoulombs, or d minus x. D minus x means 12 minus 2.4. That is nothing but how much it is? 9.6 centimeters from minus 8 microcoulombs. When you consider in between the line joint with the two charge, because already we have taken smaller charge is plus 2 microcoulombs and this is minus 8 microcoulombs and this 12 centimeters. This is applicable from the smaller charge or from the bigger charge. And the second one, outside. For second question, the same thing, outside the line joining the two charges. For this, outside the line joining the two charges, what you have to do? Here, x is equals to d by q2 by q1 minus 1. That is, it is 12 by 8 by 2 minus 2 ones and 2 fours. That is 12 by 3, which is 4 centimeters. Therefore, x is equal to 4 centimeters from plus 2 microcoulombs. Whereas the other one is d plus x, that is 12 plus 4, 16 centimeters from minus 8 microcoulomb. This is how we have to calculate the zero potential point when two unlike charges are given. This is about the zero potential point. Thereafter, some important key points related to this. Already we said that the electrostatic force is a conservative force. Any conservative force can always be given by the negative of potential energy gradient, which we already discussed in mechanics, in work per energy, whenever it's a conservative force. So, for a conservative force, F is always given by minus dU by dr. That is the negative of potential energy gradient is nothing but the force. And once you got the idea of this is the scalar form. When you ask this in a vector form, that is a vector form of conservative force. Vector form of conservative force is given by F bar is equals to minus of I cap into dou U by dou X plus J cap into dou U by dou Y plus K cap into dou U by dou Z. Here, dou by dou X, comma, dou by dou Y and dou by dou Z are partial differential operators. In this partial differential operator, generally if U is a function of X, Y, Z, then if it is a X only, if it is differentiated with respect to X, Y and Z should be taken as constant like that. That is a vector form of the conservative force. If that is the case, the third point here, Point number 3, if Q naught is the test charge, and capital E is the electric field intensity, then the electric force is given by how much it is? F is equals to Q naught into E is the electric force. But we know that F is equals to minus du by dr. But F can be written as here Q naught times E, which is nothing but minus d by dr of. This we can write it as Q naught times V, because this electrostatic potential is nothing but potential energy per unit test charge. Therefore, U can be written as V into Q naught. Therefore, Q naught times E is equals to minus Q naught into dV by dr. Therefore, this Q naught cancel. Therefore, E is equals to minus dV by dr. This is the relation between the electric field intensity and electric potential gradient. And once you got the idea of this, once you got it, then another point, that is vector form of electric field intensity you can write that as E bar is equals to minus of I cap into dou V by dou X plus J cap into dou V by dou Y plus K cap into dou V by dou Z. Once you got this, is another formula related to this. Or otherwise, here we can write another important formula there. Here E is equals to minus dV by dr, which you can write dV is equals to minus E bar dot dr bar. Because E bar and dr bar are vector, the dot dot must always be a scalar. So dV is this. Therefore, V can be written as minus integral E bar dot d bar. This is another formula that we have to use. These are some important formulas related with the, once you got, so the relation between the electric field intensity and electric potential is E is equal to dV by dr. Okay, this is the point related to this. Then how to calculate, this is about the relation between these two. Then what is the expression for the potential energy of an electric dipole in a uniform electric field? That is expression for electrostatic potential. Electrostatic interaction energy of an electric dipole, in uniform electric field. Then now come to the other one. What is the expression for the electrostatic interaction energy of an electric dipole in a uniform electric field. For that, let us consider let us say this is minus q, this is plus q. Now, this is an electric dipole of length 2L is kept in the uniform electric field of intensity E bar. Now, consider this is V1 and this is V2. This is making an angle theta, let us say. Then how to find out the interaction energy or electrostatic potential energy of an electric dipole in the uniform electric field? So for this, what you have to do, consider an electric dipole of length 2L is kept in a uniform electric field of intensity capital E at an angle theta to the lines of force. As shown in figure. This is the first thing we have assumed. So, this is an electric dipole of length 2L is kept in a uniform electric field of intensity capital E at an angle theta to the lines of force. Now, let V1 and V2 are the equipotential surfaces at which the charges minus q and plus q are placed. At which the charges minus q and plus q are placed. So here there is an important point here. This V1 and V2 are the equipotential surface. That we'll discuss later what is meant by this equipotential surfaces. Equipotential surface means it's a three-dimensional space at which the potential at every point is same is called as the equipotential surface. So minus Q is at one equipotential surface V1 and plus Q is at the another equipotential surface Q2. Then what you are going to get here is now, first of all, what to do is the potential difference here. It is given by now that V1 here. What is the perpendicular distance? If this is 2L, then the distance between these two is nothing but how much you can write? It is 2L cos theta. Therefore, E is equal to minus d over dx. Therefore, potential difference V1 minus V2 is equals to E into 2L cos theta is the first equation. Because here V1 is greater than V2. Therefore, V1 minus V2 is nothing but E is equal to d over dx. dx is nothing but 2L cos theta. This is nothing but. Therefore, V1 minus V2 is equals to E into 2L cos theta. But we know that potential energies at this point, U1 is given how much it is? Minus V1Q, and U2 is plus V2Q. Therefore, you can write this as du is equals to, it is given by the potential energy U is equals to U1 plus U2. That is nothing but how much you can write? V2 minus V1 into Q is the potential. Therefore, electrostatic potential energy it is given by U is equals to V2 minus V1 into Q, but V2 minus V1 is minus of E into V1 minus V2 into Q. That can be written as minus of E into 2L cos theta into Q. Therefore, U is given by minus 2L into Q into E into cos theta. That is minus P cos theta. Therefore, potential energy or interaction energy, therefore, potential energy of electric dipole it is given by U is equals to minus P cos theta, or this can be written as minus P bar dot P bar. This is the point here. Therefore, here, if theta is equals to 0 degrees, then U is equals to minus P. And if theta is equals to 90 degrees, then U is equals to 0. And if theta is equals to 180 degrees, then U is equal to plus P. This is the electrostatic interaction energy of an electric dipole in a uniform electric field. Okay, so this is an electrostatic potential energy, zero potential point and all. And now, still we have to discuss the potential at a point due to continuous charge distribution. Till now we discussed only the potential and the potential energy only for point charges. If you are asked to calculate the electric potential at a point due to continuous charge distribution, then how to calculate? That we'll discuss in the next class. Okay, thank you.